You know, there are a few inventions that truly changed everything, and the steam engine is right at the top of that list. It's the machine that literally moved the world. It powered factories. It built railways that shrank entire continents. It didn't just drive machines, it drove a revolution that completely reshaped society. But how? How did it actually turn simple steam into incredible, world-changing horsepower? Well, let's find out.
Our source material really puts us right at this huge turning point in history. We're talking about what's called an external combustion engine, and all that means is that you're burning fuel, like coal or wood, outside the engine to create heat, and then using that heat to create work inside the engine. And that simple idea, it was the breakthrough that unlocked a kind of power people had only ever dreamed of.
That really is the million-dollar question, isn't it? It feels a little bit like magic. I mean, you boil some water and suddenly you can move a 1,000-ton train. But it's not magic at all. It's just a masterpiece of physics and engineering. So let's pull back the curtain and see exactly how the trick is done.
To really get how the whole process works, we first have to understand the parts. We need to look at the anatomy of the machine. We're going to deconstruct a classic double-acting steam engine. This was the real workhorse of the industrial age.
Okay, so this diagram here is basically our roadmap for the next few minutes. And I know at first glance, it might look a little complicated, a bit overwhelming with all the bits and pieces. But trust me, we're going to break it down one piece at a time. The amazing thing is how all these parts are designed to work together in perfect harmony to create motion. Let's start with the very heart of the machine.
It all begins right here. High-pressure steam, which is made in a separate boiler, gets piped into this cylinder. Now, the pressure of that steam is incredible, and it exerts this massive force on the face of the piston, shoving it with huge power from one end of the cylinder to the other. It's just a simple, raw, incredibly powerful push.
A simple push is great, but you can't really power a wheel with just a back-and-forth motion, and that is where the crankshaft comes in. It's connected to the piston with a rod, and it brilliantly translates that linear push into a spin. Honestly, just think about how your legs push the pedals on a bicycle to make the wheels go round. It's the exact same principle, just powered by steam instead of your legs.
You see, that push from the steam isn't a constant, smooth force. It comes in these powerful pulses, these powerful shoves. So to smooth things out, we have the flywheel. This big, heavy wheel's own weight and momentum carry the crankshaft through the parts of the cycle where the piston isn't actively pushing. It makes sure you get a nice, steady, uninterrupted spin to power the machinery.
All right, now that we've met the key players, let's actually see them in action. We're going to follow a single cycle of the engine, what engineers call a stroke, to see exactly how that hot steam gets transformed into mechanical work.
This slide is perfect because it shows us the whole story at once. On the left, there's our engine diagram again. But on the right is this really fascinating chart called a PV diagram, or an indicator diagram. Now don't worry, it looks way more complicated than it is. It's basically just a graph that shows us exactly what's happening to the pressure and the volume of the steam inside that cylinder through one full cycle. Every phase we're about to talk about is mapped out right there on that chart.
The entire cycle, which happens in just a fraction of a second, can be broken down into these 5 distinct phases. It's this continuous, perfectly timed dance of pressure and motion. So let's walk through it, starting with phase 1.
First up is admission. A valve slides open and a powerful blast of high-pressure steam from the boiler just rushes into the cylinder. This is the power stroke. That pressure immediately slams into the piston and starts its journey down the length of the cylinder. Okay, now here is the really clever part, the key to efficiency. Before the piston even gets to the far end of the cylinder, that inlet valve snaps shut. This is called the cutoff. The steam that's now trapped inside is still under a ton of pressure, and it keeps expanding all on its own, pushing the piston the rest of the way. This expansion phase is where the engine really squeezes the maximum amount of work out of the heat energy in that steam. So once the piston gets to the very end of its stroke, a second valve, the exhaust valve, opens up. Now, the momentum from that big, heavy flywheel we talked about starts pushing the piston back on its return journey. And as it moves back, it shoves all of the used, now low-pressure steam right out of the cylinder. This clears the chamber, gets it all ready for the next blast of high-pressure steam to come in from the other side. And the whole cycle repeats, over and over, hundreds of times every minute. So we know how it works, but how well does it work? For the engineers of the Industrial Revolution, that was the big question. They needed ways to precisely measure and constantly improve the engine's performance, to squeeze every single last drop of power out of every bit of steam.
A really important distinction they made is between the power that's created and the power that's actually delivered. Indicated power is the total theoretical power generated by the steam pushing that piston. It's the absolute maximum possible. But, in the real world, you always lose some of that power to the friction of all those moving parts. The actual, usable power that you get at the crankshaft is called brake power. And that's the power that does the real work.
So how do you measure that real-world power? With this pretty clever device, a brake dynamometer. What it does, essentially, is it applies a friction brake to the flywheel or to the output shaft, and it measures the force it takes to slow it down. It's a direct, practical way to measure the engine's true, useful output.
So the next big challenge for engineers was, how do we get more brake power from the same amount of steam? The single biggest leap forward was a concept called compounding. And the idea was simple, but it was absolutely revolutionary. Instead of just using the steam once and then throwing it away, they thought, why not use it again?
And this diagram shows exactly how they did it. High-pressure steam goes into a smaller cylinder first and pushes its piston. But instead of being exhausted out into the air, that now medium-pressure steam gets piped directly into a second, much larger, low-pressure cylinder to push another piston and do even more work before it's finally let go. It's kind of like getting a second push for free. Just a brilliant way to boost efficiency. Now, it's really easy to think of the steam engine as just a piece of history, right? Something you'd only see in a museum chugging away in a corner. But you'd be surprised. The fundamental principle is still incredibly relevant and useful, even today.
Our source material points out that for certain heavy-duty jobs, steam is still king. It's just so reliable, it's simple to build, and it has pretty low maintenance costs. So it's still the perfect choice for things like driving massive industrial pumps and compressors. And its ability to provide both motion and heat makes it ideal for big facilities like hotels and laundries. The age of steam isn't really over, it just works quietly in the background now.
When you boil it all down, the story of the steam engine is a simple but incredibly powerful equation. Heat creates pressure, and pressure creates motion. That one idea completely changed our world. And as we look for new ways to power our planet today, it leaves us with a really big question. What other fundamental principles, what other invisible forces are we just beginning to understand? And what will they unlock next?